Homework 32.
Yeah.
517, section 8.4. We're moving through chapter 8. We are not going to do 8.5 and 8.6. And I don't think we're going to do 8.7.
Okay.
Not that they're not good. I recommend that you, in fact, I think what I'm probably going to do next class is say, instead of read all of those sections, rather like browse them, and so that you get an idea of what that stuff is, but we're not going to jump into it. But then we're going to go to 8.8 after that. But anyway, so plugging right along, 8.4. Number 7 through 37, odd, 51, 57, and 59. 57 and 59 are kind of, you have to do 57 in order to do 59. They can be tricky, but I'll just say one thing you'll want to remember for 57 is the cosine 2 theta is, well, and remember where this comes from. So we have cosine squared theta is 1 plus cosine 2 theta over 2. We could rearrange this to get cosine squared equals 1 plus cosine 2 theta. And then 2 cosine squared 1 theta minus 1 is cosine 2 theta. You're going to need that. Ditto with sine, which can be written a little differently. Sine theta, cosine theta. They come from the same place, but yeah. Right. So those identities here will be useful for that. But aside from that, it's still pretty difficult. Lots of stuff to keep in to do. But that's your big hint for that one. Okay? Okay, so here's the problem. And I had Noah work on this before we started. So if you're watching the video, pause the video and just try that. And first thing Noah said just a minute ago was maybe a trig substitution. And yeah, you know, and this is what I was thinking about this, is you could complete the square on this guy. And if you do that, you end up with x minus a half squared minus 9/4, which you could write as 3/2. The problem, though, is and then you do some kind of u substitution, so you would have something like this.
Wait, isn't it just x plus 1 times x minus? X plus 1 times x minus 2 for factoring it? You don't have to complete.
Oh yeah. I'm just saying, but this is something I thought of.
Oh, okay.
Why? Because you have something squared, right? Something squared minus something squared.
Oh.
And I'm thinking, if we did something like that, then that kind of leads to some kind of trig substitution. But that would be in the case where you have a root. Now, if it were plus, then yeah, trig substitution would be great, because this would be some kind of arctan thing. But it happens to be a minus. So that's only going to work if that minus is in a root. So maybe you could do something like this and do some kind of trig substitution. I don't know, maybe. And maybe that'll bear some fruit. I don't know. Noah said factor the bottom. And, okay, let's try that. So we factor that guy out. We'll have an x and an x. I'm guessing a 1 and a 2.
And plus 1 minus 2.
Plus 1 minus 2 will do it. Okay, cool. Now what? My guess is maybe a u substitution. Maybe. I'm going to go, and I'm going to choose one of them to be the u. So we have x plus 1, so that du is just dx. That's nice, but now I need to get that. So I need an x minus 2. If u equals x plus 1, if I minus 3 from both sides, I get u minus 3 is x minus 2. So I get 3u minus 3. I'm still kind of in this problem. I mean, maybe I go on from there, but I still kind of have a problem that I have a polynomial in the bottom, and kind of go back and forth with that. Like, it seems a little bit easier to deal with. But then what do you do? Another substitution? Well, then one's just going to be plus 3 and minus 3. That, you know, whatever the v, I guess, you let that be v, then that's v plus 3. And then now you're in this situation. It doesn't seem to be getting any better, right? So, okay, now let's just pause for a second. Forget about this problem and let's consider a different problem. Forget that I ever said anything about this, and let's pretend that the first thing I wrote up on the board was this. And I said, do that. Can you do that?
Yeah.
Okay, what would it be?
Wait, it would be.
And I would, that's the first thing I would do, right there.
Yeah.
Right. And so what's that? And of course there's a dx
X
there.
minus 2 to the negative 1.
Yeah. So that's x minus 2 to the negative 1, but what's the integral?
So then there'd be negative 1 times x minus 2 to the negative 2.
No, you're thinking the wrong way. This is the
yeah.
only one that does this. What's the integral?
Sorry,
of
that would
that?
be 1 over.
How about this?
Oh yeah.
Yeah, this is the only one that's weird, right?
Yeah.
All of the others, if this were x minus 2 squared, then you'd say, well, that's the same thing as x minus 2 to the negative 2. So when you integrate that, then it goes down by, you add 1 to that.
Yeah.
X minus 2 minus 1. But then it would be minus, you divide by the negative 1, so minus that. This is the only one that's weird. And so, now you could go through and do a u substitution here. The cool thing about this being just plain old x is that if you did a u substitution on this guy, watch what happens. So I have x minus 2 dx. U is x minus 2. du is just dx. And so this is the same thing as 1 over u, which is just log u plus a constant. But u is just x minus 2, log x minus 2, plus a constant.
Yeah.
And so it's kind of nice if there's no, if it's not like 2x minus 2, and even if it is, let's say it were 3x minus 2. This would be 3x minus 2. This would be 3 dx. So I would just divide through by 3.
Yeah.
Right? And it's kind of like when you have cosine 2x and you take the antiderivative of it, you know that the 2 has to go into the bottom, right? So you just go, well, it has to be 1/2 whatever the antiderivative of that is, and so sine 2x, and then you check it, you take the derivative, and the sine goes to cosine, the 2 comes out, kills the 2, and you get your cosine back. And so it's kind of the same thing with these, right? As long as it's a linear factor, then you could just kind of do that part in your head and say, well, if the 3's in front of the x, he's going to have to come out. And then you finally check it. Sorry, that should be a 3x minus 2. You do the checking, you take the derivative, you get 1 over 3x minus 2, multiply by whatever this, I'm sorry, I'm not bringing my third in here, sorry about that.
Yeah.
Right. Okay. Then you'd have your 1/3 out front, multiply by the derivative of the inside stuff, the 3's cancel, and you end up back with where you started right here. Okay, cool. Yeah. So we're going to do that a lot today, where if we have a linear factor in the bottom, I'm not going to bother with the u substitution, for the same reason I'm not going to bother with the u substitution here. So hopefully it won't be too confusing. But here we go. So this is 1 over just x minus 2, so it must be just log x minus 2. I check it, take the derivative of that. Do I get that?
Yeah.
Yeah. Minus antiderivative of this is what?
Log x plus 1.
Guys, I need you to keep it down. Thank you. And you can check, take the derivative of that, and you get that.
Yeah.
How are these things related?
Oh, the log. You can.
Well, wait a second. Wait. So first off, this is the antiderivative of that. We're good.
Yeah.
How is this related to that? Watch this. First off, let's see what happens if I get a common denominator.
Yeah.
In order to get a common denominator, I'm going to need to multiply the top and the bottom by this thing here. X plus 1. Now we have our x plus 1 there. Now, this is minus. To get a common denominator, I'm going to need to take the top and the bottom and multiply it by x minus 2. X minus 2. So this is the same thing as I got my common denominator, x minus 2, x plus 1. The top is 1 times that, so that's just x plus 1, minus 1 times x minus 2. You with me so far?
Yeah, and so it's just the same.
And it is the same thing, right? You have your x minus x is no x's. 1 minus negative 2 is 3. And you end up with the exact same thing. So I think we could agree that this problem is much easier to approach than trying to be creative with this, right? So then the question becomes, how do I go from this to this? And that's what we're dealing with today. That process, taking something with, and in fact, this is more general, because what if I had something like x cubed plus x minus 1 on top? Oh boy, like, then you got some problems, right? And it's like, if I'd started with that, this would be much harder, but this is the type of thing that we're dealing with. We have a rational function, right, which is a ratio of 2 polynomials. And the question is, can I take this thing, in this case, it's this, can I take this thing and split it up? Maybe if I factor the bottom, can I split it up so that I get each one of the factors by itself? Because if I can, it's really easy to integrate, right? And that's the goal. And this, by the way, is called partial fraction decomposition. This is a fraction.
Yeah.
These are partial fractions, and we want to decompose our fraction into partial fractions. Okay? Now, last time I said trig substitution is most commonly the hardest thing. Like everybody who takes integral calculus says that trig substitution is the hardest thing. I said you probably think that trig substitution is the hardest thing. If you don't, then you think partial fraction decomposition is the hardest thing. So these are right up there. Or if you think that trig substitution is the hardest, you certainly think that partial fraction decomposition is the second hardest thing. So we're in for it today. Okay, now you're about to learn a tool. This is a tool. This is a hammer in your hand, partial fraction decomposition. And what you're going to do is you're going to see something like this. You're going to be given a problem like this. And because you have this tool in your hand, you're going to think, I can hit that with partial fraction decomposition. But what we're going to do is wait. Do you notice that the bottom and the top are related somehow?
It's just the derivative of the top is just the derivative of the bottom.
The numerator is the derivative of the denominator. So if that is the case, if it's the case that your numerator is the derivative of the denominator, then you could do this substitution and watch what happens. 3x squared plus 2x minus 4 dx. So that dx is equal to du over, again, the numerator is the derivative of the denominator. So this occurs. So when you do your substitution, you get your u in the bottom, the 3x squared plus 2x minus 4 on top. The dx is now du over that very thing. And so now your life is much, much, much easier. We don't have to decompose this into partial fractions. You could use the method that we're about to develop today to do all of this. And you will have wasted so much time, because this is just log u plus a constant, which is just log of this x, or u is actually this right here. And you can check, if you want to, take the derivative of that, and you get that. So, every time we're about to do one of these, the first question you should ask is, hold up, is the numerator the derivative of the denominator? If it is, your life's easy. So just because you have a hammer in your hand and something looks like a nail, don't go, ooh, partial fractions, ah! It's gonna hurt. And I'm telling you, like with something like this, it would hurt really badly to try to use partial fractions on this. So the first question we're gonna ask ourselves is, hold up, wait a minute, if I take the derivative of that, do I get that? Yeah, okay, then this will be easy.
What if it's the bottom thing is the derivative of the top thing?
Good luck. Good luck. Again, okay? Okay, so first thing I want to do. Now the second so that's the first thing that we want to check anytime you're given one of these. Another thing you want to check is this. Let's say we have something like this. X cubed plus 2x squared plus x plus 3 all over x plus 2. First question is, or the second question I guess, is, okay, so first off, if I take the derivative of that, I don't get that, so that's not going to work. Second question is the degree of the numerator greater than the degree of the denominator?
Yes.
Yeah, it is. So that means we can divide these guys. If you remember polynomial long division, we take the top, like this, and we divide by the bottom.
Put it away.
Now I will try to remember to include a link in the description to my video on polynomial long division. Hopefully seeing an example will refresh you enough to just go along with it. But if you want some more, I'll try to remember to link to a previous video on that. So we ask ourselves, what do I need to multiply this guy by to turn him into that thing?
X squared.
Okay, so I put an x squared right there. Then I do that. I take him and multiply him through here. I get x squared times x is, and the first thing I do, if you remember my method is, I use parentheses here and put a minus. And so that guy hits that guy and gives me an x cubed. That guy hits that guy and gives me a what?
2x squared.
So plus 2x squared. Now that I'm done with that, I actually do the subtraction. So x cubed minus a positive x cubed is 0. 2x squared minus 2x squared is also 0. So I'm going to drop these guys down. If it were something else, I would have something else here, but I don't, because this is nice. Now, what do I need to multiply this guy by to get this guy here? 1. So I'm going to go plus 1. Then I do the multiplication. He comes down, I multiply, oh wait, first I do that. Then he comes down, hits him, and gives me x. He hits him and gives me plus 2. Now I actually do the subtraction. X minus x is gone. 3 minus 2 is, okay, is the degree of this less than the degree of that? So we're done. So this means then, right, just like when you take 5 divided by 2, you go, okay, 5, 2, how many times does this go into that? Well, 2 times. 2 times that is 4. Minus off, is that less than that? Yeah. So that means that this is the same thing as 2 and 1/2, right? Same thing here, right? So we would say 5/2 is the same thing as 2 plus whatever this is, the remainder over the quotient. Same thing here. We say this divided by that, and I'm going to put this in my integral here. This divided by that is that thing, right? That's just like my 2. You get this, and I'm going to write it as 1 plus x squared. Why would I do that? X squared plus 1. Why would I do that? X squared plus 1. It's that thing. And then I add the remainder over the denominator. And if you're so inclined, you could go ahead and multiply this, the top and bottom of this by x plus 2, the top and bottom of that x plus 2 to get, and then so you get a common denominator, combine them all, and check that you get that. It's true, it does, it works. Same way as if, well, I need a common denominator here, I multiply the top and the bottom by 2. So I get 2 times 2 plus 1 all over my common denominator. I have 4 plus 1 is 5, 5/2. It's going to work the same way here, right? Now, part of this is like, if this degree is higher, like if this were, say, squared, you might end up with something like an x plus 1. And then you can't do it anymore because the degree is greater. So the algorithm terminates, but then you would have an x plus 1 over x squared plus 2. In every case, you're going to end up with a fraction whose degree is greater in the denominator than it is in the numerator. Okay?
Unless it divides evenly.
Right. Right. Unless it divides evenly, in which case. And if that's the case, this is something I didn't put in my notes. But obviously, if you have something like this,
So if you can just factor it. Yeah.
just factor it out, right? If you can factor it out, please do that, and that's going to make your life easier. Otherwise, now we have. So what I'm saying is, you give me any rational function, then you could use polynomial long division to turn it into some expression that's a polynomial, and then something whose the degree of the top thing is less than the degree of the bottom thing. And that's what we're going to focus on today. When you have this thing where the degree of the top is less than the degree of the bottom, what do we do with that? If you have something like this, do this. And in this case, it happens to be really easy because we can just integrate like that. And let's figure out what that is. What is this integral here?
It's 1/3 x to the third plus log of plus x.
Yeah, don't forget about him. Plus
Log of x plus 2.
there we go. Plus a constant. And that's your answer. That's what this guy is. And you could take the derivative and get your stuff and figure out, yep, that's gonna... And you can see, if you take the derivative of this, you get this. And if you're so inclined, you could go ahead and put all those together. X plus 2 on the top, x plus 2 on the bottom. X plus 2 on the top, x plus 2 on the bottom. Combine everything and you'll get that. Okay. So what we're going to focus on now is integrals of the form. It's a rational function where the degree of the bottom is bigger than the degree on the top. If it's one like we just saw, start with polynomial long division. Now, I'm going to skip all of the theory of this. Like why, everything I'm about to say, like, basically, there's, what we have are 4 cases for when you have some p of x over q of x, and you want to take this thing and decompose it into partial fractions. And depending on what q does, we have 4 cases that we're going to talk about. And I'm just going to say them kind of as rules instead of delving into the theory of why these rules apply. But we're going to do examples and you'll see. And it's kind of weird. If we had more time, I would go into why it has to be the case. But I don't think it's really necessary to go into that. You'll see why it has to work, kind of. So, but I don't want to waste too much time on that. So I'm going to write out all the different cases. So you have something like this, and you want to turn it into some kind of thing with polynomials on the bottom. Right? Yeah. There are 4 cases. And we're going to go through each one. Case 1 is where q factors into distinct linear factors. So a1x plus b1, a2x plus b2, and so on. Okay? Now, one thing, so this is the case where q factors into distinct linear factors. And they're all different. Okay? None of them are repeated. Okay? One thing to keep in mind is that x itself is a linear factor. It just happens to be the case where it's 1 plus 0, like that. That could trip you up, but anyway. So that's one scenario. Case 2. Again, we're going to do examples of all of these. Is q factors into linear factors, but some of which are repeated. So what that might look like is you have something like this, And then you have an a2x plus b2, but that's raised to some power. So that is, they're repeated, right? And then you have like an a3x plus b3 and so on. So for instance, if you have like 2x plus 1, x minus 3 squared, and then like a, I don't know, 2x minus 5. That would be this kind of case. So linear factors, some repeated. And maybe more than one of them are repeated, right? Maybe that's raised to a power 2. Okay? Case 3. Guys, please try to keep it down. Thank you. Okay, here we go. Q has an irreducible quadratic. So this is irreducible. Okay? In fact, what I'm going to do is more generally here, right? That is ax squared plus bx plus c, and then maybe some other linear factors, like a c d ex plus f or something like that. But where this guy, where the discriminant, b squared minus 4ac, is negative, right?
Yeah.
Because if that's negative, then the square root of it, right? Think about if it factors, the square root of that thing is negative, so it has imaginary numbers. So just like if I had x squared plus 1, you might say we could factor that. It's x plus I, x minus I. That's true. You could factor this. The problem is now you're going to be integrating with complex numbers. Completely different ball game right there. Like a whole, we need to develop a lot more theory before you do that. And so like all of these cool tricks that you're learning, actually, it turns out like you won't need to worry about any of this stuff down here when you take complex analysis. You could break them all down into linear factors because this guy will do this. So these cool tricks that we're going to learn for cases 3 and 4 that involve quadratics that don't break down, turns out you could break them down and do it. You just need to know how to do complex integration. And so, okay, so what we're going to call this is the case where Q has irreducible, has an irreducible quadratic factor. It's an irreducible quadratic factor. Okay? You might ask, well, what if it has an irreducible quartic? What if it's something like x to the 4th plus 1? We're not dealing with that stuff. Don't worry about that stuff. And like when you're ready to deal with that stuff, you're just going to factor it into its complex numbers anyway. So we're not going to deal with that kind of stuff. Okay? Okay. So what happens now? Case 4. Sorry. Case 4. We won't do an example of this, but I'll tell you how to deal with it. It's just an example would take forever, and so we're not going to do that. So, same kind of deal, but the irreducible factor is raised to some power. Okay? So it has an irreducible, or it has irreducible quadratic factors. It has irreducible quadratic factors, some repeated. So that would be QX breaks down into, I don't know, an AX plus B, and then it has like an X squared plus 1 raised to the 3rd. And then it has, I don't know, 3X plus 2, and then maybe an X squared plus X plus 1 cubed. Or squared, or whatever. Yeah. So it has more than one, it's the same kind of thing if it has an or multiple irreducible quadratic. They're going to be the same thing. Like the way we're going to treat them are the same. Yeah. Okay, boy. Okay, so Here's an example of case 1. Again, we're not going into what, I'm going to show you a rule of what to do if you're in case 1. I'm not going to tell you why. I mean, too much. I'll kind of explain it as we go along, but hopefully what we're doing here is going to make sense. So, we have an integral. And I see, so we're gonna do our checks first. I'm gonna ask myself, is the derivative of the bottom equal to the top?
No.
No, we get 3x squared minus 1, that's not the same thing. And I don't think that factors, so nah, that's not gonna help. So, can we use polynomial long division?
No.
No, the degree of the bottom is greater than the degree of the top, so if we tried, it would terminate right there. So we're done, okay? So, what I'm gonna do is say, therefore, so first off, we're gonna factor the bottom. So, I'm gonna pull out an x, so it gives me x squared minus 1. Can we factor that some more?
Yeah. It would be x plus 1, x
Oh, there you go, x plus 1. X minus 1. Think back to algebra 2. Why are we spending so much time factoring? Oh.
Yeah.
Okay, so I'm going to go ahead and factor the bottom. X plus 1, x minus 1. Notice, distinct linear factors. Okay, they're all different, and they're all linear, right? There's no squareds in there, there's no quadratics, so, okay, cool. Then what we do is we're just going to rewrite this. The idea is what I'm looking for, what I want is some x, some fraction involving x, some fraction involving x plus 1, and some fraction involving x minus 1. That's what I hope to do. The only question is, what constants give me that?
Constant.
Some constant A, some constant B, some constant C. And so, this is the equation that we want to solve. So, we have an equation that we're trying to solve. There's 3 variables, A, B, and C. And so, let me say it this way. We have an equation that we're trying to solve, and it has stuff in the denominator. What would you like to do to make your life simpler?
Kill
the denominator. So, I'm going to take the right-hand side and the left-hand side. What do I need to multiply by to kill that entire denominator?
just x times x
X, whatever the denominator is, right? So x plus 1, x minus 1. Whatever I do to that side, I got to do to this side. So x times x minus 1, x plus 1. So he distributes over. The x kills the x, and we're left with a times x plus 1, x minus 1. He jumps over, the x plus 1's cancel, and I'm left with x minus 1. This jumps over, the minus 1's cancel, and I'm left with c x plus 1. On the left-hand side, the denominator is gone, and I have this. X squared plus 2x minus 1. Now what your book says to do from here is to multiply all of this stuff out, and you're going to end up with, let's do it real quick, I don't really want to do it real quick. You end up with an x squared minus 1 here, a b x squared minus x here, a c x squared plus x, then we condense everything so we get ax squared minus a plus bx squared minus bx plus cx squared plus x. Then we keep rearranging. Get all of the x squareds together.
Right?
I'm sorry? Oh, yes, thank you. That would have messed everything up. And so I'm going to condense all my squareds, and I have an a plus b plus c x squared. All my x's, I get a, how about c minus b x minus a, like that. right? Okay, so you do this, multiply everybody out, and you get this. And then what you do is you say, well, if this polynomial has to equal this polynomial in every case, no matter what value of x I plug in, let's say that again. If this polynomial has to equal this polynomial, no matter what x I plug in, then it has to be the case that whatever this constant is in front of here has to equal this constant. So we get 1 has to equal a plus b plus c. This constant, 2, has to equal that. So we get 2 equals c minus b, or write that a bit more suggestively. Finally, negative a has to equal negative 1.
Yeah.
Negative 1 has to equal negative 2. And you could back solve or whatever. This happens to be a really simple one to solve. But in other words, you have 3 unknowns, you get 3 equations, and they're linear equations, so you have a system of linear equations and 3 unknowns. You have 3 of them, you could solve for a, b, and c.
Yeah.
That's how your book says to do it. How do I do it? This is how I do it. I'm going to think what I just said before. This polynomial has to equal this polynomial for every value of x, right? So no matter what value of x I plug in there, it still has to be true, right? So I could choose any x to plug in. So what happens if I plug in a 1? Let's just see. I'm going to let x equal 1, and I like to do this because this is going to get ugly. In this case, it's not going to get too ugly. Later on, it's going to get ugly. I like to keep track of what I'm doing here. So I'm going to say, okay, let's plug in an x equals 1. So I get 1 squared plus 2 times 1 minus 1 equals. Now when I plug a 1 into here, what happens?
0.
Aha. What happens when I plug a 1 into there?
0.
What happens when I plug a 1 into there?
2.
1 plus 1, so that's 2 times 1, so that's 2c. So we get that 2c is equal to, what does that work out to?
1.
How about,
2.
2, okay. So that gives me that c is equal to 1. So you could choose any 3 values you want. I could have chosen x equals 10, x equals 20, x equals 30, and I would have gotten 3 equations. Because, right, we have 3 unknowns, we need 3 equations, and so again, I could have plugged in a 10 into each one of these, and I'd end up with something like 100 plus 20 minus 1, so 119 equals, and then whatever that would be, it would be some number times a plus some number times b plus some number times c, and we could come up with 3 equations, 3 unknowns, and we could solve a system. Or we could choose which numbers, which make our lives easier. What's another number, given these, that might make your life easier? X equals what? X equals 0 will help. So I'm going to plug in x equals 0 into here, and I get 0, 0 minus 1 has to equal, okay, so plug in a 0 here, that gives me a 1. Plug in a 0 here is negative 1, so that works out to negative a. Plus, plug in a 0, we get a 0. Plug in a 0, we get a 0. So negative a equals negative 1 means that a equals 1.
Okay. And then negative 1 also.
And negative 1 will also help. Now you could do 2 if you wanted to. You could plug in a 2 and everything will work and you'll have 3 equations, 3 unknowns, you'll be fine. Or you could choose negative 1. So I'm going to choose negative 1. X equals negative 1. Plugging in negative 1, I get negative 1 squared is 1. Negative 2, negative 2, negative 1. Okay. Plug in a negative 1. That guy goes to 0. Plug in a negative 1. Okay, so here's where I'm going to have to be careful. So it's negative 1. Negative 1 minus 1 is negative 2. So just 2. Now, plug in a negative 1 here and we get a 0. So, here we go. 1 minus 1 is 0. Minus 2 is left over. Negative, negative, so 2b.
B equals negative.
And so b equals negative 1. Okay, so it's going to really help you as you do this to have this somewhere on your page. Because if you forgot all about this, and you go, okay, so A is, wait a minute, which one did I put first? And so you might think that A goes with the x plus 1, that B goes with the x, and that C goes with the x minus 1. Please refer back to what you did here. Otherwise, your life's going to get really hard. So, now I want to check this. This is how I like to check it. I'm going to forget about all of this over here, and I'm simply going to plug in those 3 numbers that I got into this thing right here. And make sure, and in fact, I'm forgetting all of this stuff that I did. I just want to make sure that when I put a 1 here, and a negative 1 here, and a positive 1 here, that I could add those together to get that thing right there. So, let's see what happens. A is 1, so I have 1 over x. B is negative 1, so I'm going to write it as negative 1, like that, over x plus 1. C is 1, so that should be plus 1 x minus 1. Now, in order to turn this thing into that thing, I need a common denominator.
Yeah, so multiply the top and the bottom.
So, yeah, let's give myself some room right here. So the top and the bottom, the thing that I'm missing here is a x plus 1, x minus 1. So x plus 1, x minus 1, can't change it, gotta do this, x plus 1, x minus 1. Okay, the thing I'm missing here is an x and an x minus 1. So on the top, I'm going to put my negative right there. X, which one did we do? X minus 1. Finally, the 1 I'm going to forget about. If it were a 7, I would not be forgetting about it. But now I'm missing an x and an x plus 1, so I need an x and an x plus 1. Now we have a common denominator. So I have x plus 1, x minus 1. This works out to first outer inner last is x squared minus 1. Right?
Yeah.
This is negative x squared
Plus
plus x. This works out to x squared plus x.
Yeah,
Okay, now.
the x squared.
X squared, those two x squareds are gone because this is a plus and a minus. We have 1 left over. And I'm going to go ahead and do this so I don't forget what I'm doing. Start there, okay? Now, there's 1 x squared left over, check.
Yeah.
X and x gives me plus 2 x's, check, check. I'm left over with a minus 1. Is that what we started with?
Yes.
Oh, lo and behold. Okay, so let's make sure I erased everything, but I believe this was a 1, this was
I
a
think it was in
negative 1, and this one was a 1. So now I can integrate. I've checked it. I'm sure that this is the same thing as that. And so I'm going to integrate.
So it's just
And so here we go. I integrate here. Same thing as integrating here. What's the antiderivative of 1 over x?
log of x.
Log x.
And minus log of x.
Minus log x plus 1
Plus log of x minus
plus log x minus 1. Whoa, there we go. Not bad. Now you could, I don't know what it looks like in the back of the book. Wolfram Alpha says this, so I feel good about that. But properties of logs, add 2 logs together, that's the same thing as multiplying the inside stuff. And subtract logs from each other, it's the same thing as dividing. So your answer might look like this in the back of the book. And so if you do all this work and you get to here and you go, okay, let me check the back of the book and you see that, you're right, you're still right. It's just that they rewrote it.
Yeah.
Okay, so that's what you do if all of them, so note, if all of all of the factors are linear and they're distinct, then they breaks down into just constants. You do each one of them one time, and then it's just constant A, constant B, constant C. Why? don't want to get into it. But it comes down to this thing, right? It has, if you've divided a polynomial by another polynomial and you're in its reduced form, then the thing on the top has to have 1 degree less than the thing on the bottom.
Yeah.
And so it must just be a constant. So there you go. That's what it comes down to. There's a bit more to it, but who cares? So, okay, case 2. We're not even to case 2 yet. This is going to be a long one, I'm sorry. If you need to go, you just let me know that you need to go. You could mess these up. So I did a bunch of work and realized, oh no, I made something negative and I had to do it all over again. So here's case 2, number 20. So we have x squared minus 5x plus 16 all over 2x plus 1 x minus 2 squared. Linear factors, but one of them is repeated. Okay? They're all linear, there's no quadratics down there, but one of them is repeated. So, the thing we're going to do, same kind of thing. 2x plus 1, x minus 2 squared. The way you write this is that this first linear factor, he's not repeated, so it's the same thing. 2x plus 1, some number a.
Yeah.
The next one now, it might be the case that he's just there by himself. And in that case, he would have to have something like that. Or he could show up as squared. And so this is what you do.
Oh, and one of them just might be 0.
Well, it's just this is what you do. Like I said, I'm not going to get into the theory, like the ins and outs of why this is the case, but this is the thing to remember, that if you have repeated ones, you just climb up, basically. So if that were to the third power, right, then we'd say, okay, x minus 2 to the third, and we put another constant there.
Oh, okay.
You could deal with all of this by just saying, okay, and if it were to the third, which it's not, but we're going to pretend for a second that it is. If it were, you could say, okay, then this has to have 1 degree less. So it has to be an ax squared plus bx plus c. But then you'd break this down and say ax squared, x minus 2 to the third, plus bx, x minus 2 to the third, plus c, x minus 2 to the third. But then, since these are just constants, then you could factor this out and do the same thing, and you end up with, after rearranging a bunch of stuff, you end up with saying, oh, like, this rearranges to like an a plus b plus c with that, and then that ends up with a b minus c, blah, 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 and what you end up with is something that looks like this. So it's just, we're skipping a lot of, basically you start here, play with a bunch of stuff, and you could use different values here, like, I don't know, n, m, and l, and then you do some stuff and you find that what this thing looks like when you've broken it down is some kind of x minus 2 to the n squared plus ml or whatever plus whatever the x minus 2 squared n plus m times l, and stuff like that. But then since those are all just constants anyway, you could just jump to the chase and do that.
Yeah.
So this is just, like I said, I'm just going to tell you a rule. The rule is that you do this. Why it's like that, I don't want to waste time. But this is what the rule ends up giving you right here. Or this rule ends up just cutting to the chase and saying, well, what you end up with is something that looks like this. And since that's the case, let's plug along. Same thing we're going to do as before. We have an equation with denominators. Now here's the thing. You can't just say, oh, well, let me just plug in a 2. because they're in the denominator,
Yeah.
right? And this is probably why the book says not to do this, because technically, this is the thing you're working on. You can't just plug in a 2. But when we multiply out, guys, please, please. Once we multiply it out, they're no longer in the denominator, and it just turns out to be that. Well, here, let's do that, and we'll talk about it. So I'm going to multiply by the denominator here, leaving me x squared minus 5x plus 16. Multiply through by the denominator here.
And then you get
One of those
x minus 2
cancels.
squared times a.
There you go. X minus 2 squared.
And plus
Now.
bx minus 2 times 2x plus
So there you go. So 2x plus 1, x minus 2.
1. And
Finally,
then
C.
2x plus 1.
He cancels with that, and then we get
Yeah.
2x
No, plus 1.
plus 1. Thank you. And so now it's kind of like, now you can plug in a 2 if you wanted to. But it's just like, technically you really shouldn't, because this is what you're working on. But now we're just saying, well, this polynomial, whatever it is, has to have the same coefficients as this polynomial, whatever it is. It has to be true for all values. And so if you find, it's kind of like, well, we have a lot to do. So we could multiply all this out. I'm not going to do that. I'm going to try to choose my stuff wisely. Which x do you want to start with here?
2.
If x equals 2, then this is 2 squared is 4, minus 5 times 2 is 10, plus 16. That kills that.
Yeah.
That kills that. The only thing I'm left with is c times 4 plus 1. So that's 5c. This is 10, I think.
Yeah. Yeah.
Right? 16,
it's 20
minus, yeah, it's 10. So that means that c equals 2.
Yeah.
Okay. Now, what's another x you want to choose?
Negative 1/2.
-1/2. Why? Well, because that's going to make my life easy. If I plug in a -1/2 into here, that makes that 0. Ditto right there. Nice. So, -1/2 squared minus 5 times -1/2 plus 16 equals. Okay. -1/2 there. Okay. -1/2 minus 2 squared. It's the same thing as that. Oops. Was that? So that's -5/2. Right? Squared is 25 quarters. So 25 quarters A. And then those guys are gone. By design. That's why we chose that right there. He's gone. He's gone. Nice. Okay, cool. So, now there's a bunch of ways we could do this. I chose to do it this way. We have a quarter minus plus 5/2 plus 16 is 25 quarters. I multiply both sides by 4 to give me 1 plus 4, 10. 16 and 4 is 64. 25A. You can do it any way you want. Who cares? This works out to 75 equals 25A. So that A equals 75 over 25.
Just 1/3.
Is, how about 3 ones?
Oh, wait.
75. I don't. I think I actually wrote 1/3 when I did this. So A equals 3.
Yeah.
Let me check that. Make sure I didn't. Yep, A equals 3. Oh, that's the one I did wrong. Yes, A equals 3. Okay, so now there's not a nifty one we could choose, right? Like that, we chose ones that helped us because it made those drop out. But now with these repeat, and you're going to see this when you have repeated roots, life gets hard, and especially the more they're repeated. Like if this were to the 5th,
The
the harder it's going to be. But
0, I guess. It's probably not that hard.
there you go. You could choose any of them. Any number, because it has to work for every single value. This has to be true. So, let's do it with, you said 0. Let's do 0 and see what happens. If x equals 0, I like 0 because that makes this easy to compute.
Yeah.
0 and 0, that's just 16. Plug in a 0. Now, so that's
It's just
0 minus 2 is -2 squared is 4, so 4a.
And then
0, so 1,
like times
negative
minus
2,
So negative 2b.
negative 2b. And 0 and 1, that's nice. C.
Okay.
Now, we know what A and C are. So let's just cut to the chase here. 16 is 4 times 3 minus 2 times 2 plus C. 16 equals 12 minus 4 plus C. 4 makes that 20. 12. C should equal
8.
uh-oh. Because we weren't solving for that. That's what, look at what I did. C is 2, not B.
Oh.
A is 3. Okay, 16 equals 4 times A is 3. See why people hate this? This is why people hate, because,
Yeah.
okay, so that's 12 minus 2b plus 2 equals 16. 14, bring that over, and you get 2 equals minus 2b, so that b equals negative 1. Yes, that's what I got. Now, we plug that back into here, and we get b is, so let's start with the a. 3 over 2x plus 1.
Yeah.
B is minus, so I'm going to write that as minus 1 over x minus 2. And then C is 2, so that's plus 2 over x minus 2 squared. Now, we could check that. It's going to take a lot of time if we do. But you could check it. I checked it. It works, right? You just get just get a common denominator. You're missing an x minus 2 squared. You do that there and there. Here you're missing an x minus 1, so you do that there and there. You're missing another x minus 2, so you got to put him there and square him, etc., etc. Please check, because this is what's going to drive you nuts, is you get something, you didn't check it, you do more work to get the antiderivative, and then... So just take the time and check it, and your life will be so much easier. So, the integral of x squared minus 5x plus 16 over 2x plus 1, x minus 2 squared dx is the same thing as the integral of 3 over 2x plus 1 minus the integral of 1 over x minus 2 plus the integral of 2 over x minus 2 squared. That 2, okay, I'm just going to think in my head, right? If I did a u substitution, 2x plus 1, then the du would be 2 dx, which means I would need to divide by the 2 when I change over to u. So, but everything else, don't need to worry about. So the 3 comes out, I would have to divide by a 2, and then it should just be log u. But u is 2x plus 1. So this is kind of how I do it in my head, right?
Yeah.
I see like, oh, there's a 2 there, so he's going to need to go. Then I check it, right? And I take the derivative of this. That goes into the denominator. Okay, so 2x plus 1. The 3 halves is still there. Then I have to multiply by the derivative of that, which is 2.
Yeah.
And so I'm back where I started. Okay, I'm good. This one's not hard.
Just minus log of x
Minus
minus
log of x minus 2.
2.
Check it, take the derivative, you get that. Yes. Now this, you might think, it's a log, or you, wait a minute.
No, it's to the negative 2.
Yeah, and so this is this right
Yeah.
here. X minus 2 to the negative 2.
So that's
It would have to have been a negative
1.
1.
Negative x minus
Negative.
2.
And so the negative 2, x minus 2 to the negative 1 should be the derivative, or the antiderivative of that. So I'm going to take the derivative of this. The negative 1 drops down, gives me a 2. Yes. That goes down to negative 2. Yes. Derivative, or yeah, multiplied by the derivative of the inside is just 1, so that works. So this thing right here should be minus 2 times that, and I'm going to write it like this. Plus a constant. Let's see if that's right. 3/2 log of that stuff, yes. Minus log of that, yes. Minus 2 over x minus 2 plus a constant. And that is what Wolfram Alpha tells us it is 2. Okay,
What's case number 2?
that was case 2.
We're halfway done.
We're halfway there. And actually, we're not going to do an example for case 3, or case 4.
Okay.
But I'll show you what to do. And it should, by the time we get there, you should expect it. You should get it. So, here we go. Case 3, number 28. We have an integral. And let's see, x squared minus 2x minus 1 all over x minus 1 squared. And now we have x squared plus 1. So we have an irreducible, we have one irreducible quadratic. So first off, is the top the derivative of the bottom? Real quick, I could see that when I multiply that out, I get x squared. Here I have an x squared. So the degree of the bottom is going to have to be x to the 4th. Take the derivative of something to the 4th, you don't get that.
Yeah.
So no, we don't need to worry about him. What about polynomial long division?
No, because it's the same.
It's same problem, right? We have a to the 4th on the bottom, square, or to 2 on the top. That's not going to help us. So we're going to break this guy down. We are going to do partial fractions here. Minus 1. X minus 1 squared. X squared plus 1. Now the way this breaks down, same thing here. We have a repeated linear root. So it's the same thing we did before. Some constant over x minus 1. Some constant x minus 1 squared. So we don't stop using the previous rule. It's just now we're adding a new thing here. And this is where, since it's irreducible, then the thing on the top has to have degree 1 less than the thing on the bottom. Since the thing on the bottom is quadratic, then the thing on the top has to be linear. And so since I'm using A and B, I'm going to use C and D to go Cx plus D. There you go. That's all there is to it. And it's the same, it's all the same reasoning, but it's just, this is how we, this is,
Yeah.
there's no shortcut here, because you can't break him down, right?
Yeah.
Before, with the repeated ones, they could be broken down and whatever, and then it works out that you could just do it like this instead. Now it's true, you could have just said this. And then have done this. But in doing this, you can multiply out and blah, 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 and you find that that's just a lot simpler. So we're just going to roll with that. That's the rule. I'm just telling you to believe me, it works. So, okay, here we are. Now that's irreducible. We have to have degree 1 less than that. So we're going to do that. What do you think we're going to do now?
Fucking. I know,
Not
multiply
really,
everything.
I don't want to plug
Yeah.
anything in yet. So let's kill the denominators. Doing that over here gives me x squared minus 2x minus 1. What do we get over here?
It would be x minus 1 times x squared plus 1.
Yeah. So again, I basically, what goes through my head is, I'm just taking him upstairs, right?
Yeah.
And so I'm just visualizing, if I had this and I was multiplying it right here, one of them would cancel, so I have my a times, one of them's canceled, and he's still coming upstairs here. Same thing, bring him upstairs, boom, we're gonna have a b. Both of them are gonna cancel, but I'll be left with an x squared plus 1. Now here's the hard part, don't forget your parentheses here. Parentheses on that guy. We bring those guys both upstairs, the x squared plus 1's cancel, and I'm left with an x minus 1 squared. Now the book says multiply all of this out. And then, yeah, and boy, that's...
Yeah.
And you'll notice, and here's the thing, if you're really like that, you'll notice you're going to end up with cubed terms here. But there's no cubed term there. But there is, because you could always write it as 0x cubed. So that gives you another equation. Once you get everybody together, and let's say, I don't know, it looks like it's going to be ax cubed. Over here you're going to have a squared, and so it looks like another cx cubed. And so that would be a plus c x cubed. So that would have to match with that, so that gives you a plus c is equal to 0. That would be one of your equations right there. The other equation would come from whatever the squareds are when you put all of them together, and they would have to equal 1. The other one would be all the pure x terms, whatever they are, and that would have to equal -2. I don't like that, and we're not going to do that. We're going to choose our stuff wisely here. What x do you want to use first? X equals what? 1. If x equals 1, then I plug it into here, and I get 1 minus 2 minus 1. 0. 0. So all I have left is
2b.
Yeah, because 1 squared is 1 plus 1 is 2. 2b. So that means that's a -2 equals 2b.
b equals negative.
So b equals -1. Let's make sure. Yes. Okay. Yeah. Now, can't plug in an I. You could plug in an I. You could plug in an I. And then you'd have I squared is -1 minus 2I minus 1, -2 minus 2I. And then you'd have some other stuff over here. And I guess that would go away. You would have I minus 1 squared. See, jeez, I don't even want to think about it. And it would work. It would work. And everything would cancel out, and you would get exactly the same thing, but you'd be dealing with complex numbers.
Yeah.
So that's not going to work. How many, so what question, first question, how many unknowns do we have?
4, so
4, right? And let's be explicit. They're A, B, C, and D. Those are the 4 unknowns that we're trying to find. So how many equations do we need?
4.
4. How many equations do we have?
1.
1. This is an equation.
Yeah.
And because, you're thinking about, this is like, I don't know about you, but I'm thinking about a system of equations here, right? Like A minus C plus D. This is what you're working with. And if you could just get, these equations, you'd have a system of equations. And then you could just go ahead and solve them. And so, you could get them as long as you're plugging in 4 distinct numbers. Any 4 distinct numbers will work.
0 we get rid of minus 1.
Say again?
0 we get rid of the 6 plus d. Oh, no, wait.
Well, zero is going to make your life easier. 0 almost always makes your life easier. That's one that I want to use.
Yeah.
So I'm going to use 0 to get another equation here. So plug in a 0, that's nice. That's one of the reasons I like using 0. Okay. 0 here, you have a -1. 0 there, you have a +1. So that's just -a. 0 here just gives you a b. Again, 0 is one of your best friends. 0 here gets rid of a variable. How nice. Or gets rid of an unknown. That's nice. A 0 there gives you -1. Squared is +1. So how about plus d? Okay, so there's an equation. 2 equations. We need 2 more. So what x do you want to use?
Maybe just 1 or...
Well, we already used 1.
Oh, yeah. -1 maybe?
-1. -1 is also pretty nice. In fact, that's one that I used. So -1 squared is 1. Negative makes that a +2 minus 1. Okay. -1 minus 1. And then we have -1 squared plus 1. That's -2. And that's 2. So that should be -4.
Yeah.
So -4a. 2b.
Yeah.
Now, minus. Okay, so hold on. -1 minus 1 squared is 4. So that's 4 times c times minus 1 plus d. So that's minus 4c plus 4d, right?
Yeah.
Okay, let's just say again, I'm plugging in a minus 1 into here.
Yeah.
And when I do that, I should get minus 4c plus 4d. How many equations do we have?
3.
We have 3. We need one more equation.
2.
Sure. X equals 2. Plug them in here, I get a 4 minus 4 minus, wait, yeah, positive 2, yes. Minus 1. Okay, 2 minus 1 is 1. 2 squared plus 1 is 4 plus 1, so that's 5a. Again, 2 squared plus 1 is 5, so that's plus 5b. Now, that's 2c plus d times 2 minus, oh, that's nice. 2 minus 1 squared is just 1. So plus 2c minus d. Or plus d plus
2c plus d.
plus d.
Okay.
Okay, now let's get, that's an equation, that's done, that's nice. Let's clean these up. 1 minus 1 is gone, so that's just 2. 4 minus 4 is gone, so that's just minus 1. Okay, now, we could do this a lot.
Get rid of all the b's.
We could get rid of all the b's. Let's do that. If b is minus 1, then I could rewrite this guy as minus 1. This then becomes minus 2.
Yeah.
And this becomes
Minus 10. No, minus
minus.
5. Wait.
Wait a minute. What was that? That was a minus 5b?
Yeah.
Or no, it was a plus 5b. And so now it should be minus 5.
Yeah.
Let's make sure. Let's make sure. Because he was plus 5b. Plug in a negative 1 gives you a minus 5. Okay. Okay, so let's see what we could do. First off, with this one, add 1 over there and you get 0 equals minus a plus d. So that means that a equals d.
Oh, so now all the
That's nice.
d's.
Now you could set up a matrix. You could just do this with a matrix
Sure. Yeah.
if you wanted to. It's just that I happen to notice this right away and like, well, okay, hold up. This is gonna make these easier. Because watch what happens. If a is equal to d,
Replace all the d's with a's.
just replace the d's with the a's. That makes this easier, because look at this. Minus 4a plus 4a. One thing you don't want to do, though, if you're going to do what I'm doing, don't start going backwards and working with other ones that you have. Always go in one direction if you're going to start substituting. Otherwise, you're going to end up in a loop, basically.
Yeah.
So, okay, hold on. Let's see what we have. 2 minus 2. 2 equals minus 2 minus 4c. So that's 4 equals minus 4c. So that means c is equal to negative 1. Nice. C is equal to negative 1.
And you can just plug that into the last one.
Into the last one. You don't want to go backwards and plug it into one of the... And we've even erased them, so who knows what they said to begin with. But you want to keep going forwards, right? And so that's what I'm going to do here. I've already done the B. I've already done the D. Now I'm going to do the C. So if that's minus 1, then this turns this into a minus 2, like that.
Yeah.
So that's 6 A's. That's minus 7, minus 1.
So
Add that
6.
over. I get positive 6 equals 6A.
Equals 1.
So that A equals 1. The only thing left is D, but we know that A equals D.
Yeah.
So
D equals 1.
D equals 1. Now, let's put everything back. Okay. Whoa, chill out. Please. I don't want to erase my answers here. Be really careful. Okay, so let's put these back into here. A is equal to 1, so we get 1 over x minus 1. B
is negative 1.
Negative 1. So plus negative 1 over x minus 1 squared. I'm good with him. C is negative 1, so that's minus x. D is 1 plus 1 over x squared plus 1. Okay, let me make sure that's what I got. And I did, yes, 1 over x minus 1. Negative 1 over x minus 1 squared plus negative x plus 1 over that. Yes, and I did check it. Trust me, I got them all with a common denominator. Right? Multiply this guy by x minus 1 times x squared plus 1, top and bottom. Over here, x squared plus 1, top and bottom. Over here, x minus 1 squared, top and bottom. You do it all, and it does come out to that. Actually, what happened is it didn't work out. And then I realized I had all of this written down, and when I went to do it, I thought that C was 0. And so I had this. And I did a ton of work and realized, oh, I did it wrong somewhere, and then finally realized I just didn't copy the C the right way. So this is, as you can see, this is why some people hate this more than anything else.
Basically, a lot of it's just algebra.
It's just, the hardest part of calculus is the algebra.
Yeah.
By far. By far. Because that's what's going to mess with, right? Like, you're not doing anything conceptual here. It's just like, well, if I could rewrite this like that, I could integrate it. It's easier. Like, there's no, like, big mind calculus going on here. It's just I need to take an integral. How do I do it? Like this. Oh, yikes. So, let's integrate this bad boy. Integrate. Same thing as, I'm going to pull that negative out and integrate here. And this guy is going to be where it's hard.
You have to do the same thing again.
No, you could. But I have a better way. And I'll show you what to do when you end up in this scenario. Because worst case scenario, right? You end up with an ax plus b on the top, and then some quadratic down here, right? Some kind of quadratic. And what you could do, and this is what we're going to do, is just break them up.
Quadratic.
Like this. And your life is probably going to be easy.
Oh, yeah. That'll be easy.
It'll be way easier. And so that's what we're going to do. So, the first one, what's this one work out to?
Log of x minus 1.
Log of x minus 1. Now, this one's weird because
Yeah.
you think it's log, but it ain't. Right, so you have x minus 2 to the negative 2.
So it would be
So it's x minus 2 raised to the,
negative 1. So
and we have to make it negative. And so, he's a negative. So that's going to make it positive. Positive, that stuff, is the same as that. I'm just going to check. That's negative 1. He comes down, makes that negative. Good. Then you bring it down to negative 2, which brings that guy into the denominator. Okay, good to go. Now, here's the hard part. Uh-oh. We're going to have to do this again. Yeah, but he's irreducible. That's always going to happen when he's irreducible. It's going to be like that. So, what we're going to do is rewrite this as plus the integral of negative x over x squared plus 1 plus, I'm going to break them up again, integral 1 over x squared plus 1. Each dx, not going to worry about it. Is the top thing the derivative of the bottom thing? Not exactly, but you're off by a constant.
Oh.
Yeah, be careful with that. Watch what happens. du is 2x dx. So that dx is du over 2u. And so, I'm going to substitute here and get negative x over u dx, which I don't have in there, is du over, I'm sorry, 2x. It's a 2x,
oh, yeah.
and I brought him down. It's about to say, no, it's u squared. Oh no, and I still have an x. So 2x. So the negative comes out, the x's cancel, and I could rewrite that as negative 1/2 1 over u, like that.
Yeah.
So that's negative 1/2 log u, which is negative 1/2 log x squared plus 1. Yeah, it's, and again, you're learning a new technique, so you see that and you go, oh, I'm gonna hit it with a hammer. You get hold up, wait, we've done these before, right?
Yeah.
We've split up numerators. I mean, you could do that with each one of these. You could split up this numerator and then treat it as 3 different integrals. That's cool too. I mean, whatever. But
I think that's hard.
I think it would be.
Yeah.
So I want to make sure I'm recording all of this. Log x minus 1 plus 1 over x minus 2. That we found out works out to minus 1/2 log of that stuff.
Yeah.
Minus 1/2 log of x squared plus 1. Now this should be easy to check. Let's just check it. Take the derivative of this, it goes into the denominator. Check.
Yeah.
Then multiply by the
inside
derivative of the inside stuff, which is 2x.
stuff.
And so you have a 2x on top. The 2 cancels. The negative. Yeah. Okay. Yeah, we're good. What's that one?
Wait, I've done this one.
You have done this one. We derived what this was. And this is the thing. Now you're thinking of your hammer, and you're like,
Oh, right.
oh yeah, right. And you're gonna forget about him. And this is another reason why this is so difficult. Is you've got this big hammer, and everything that you're gonna end up with in the end are polynomials. So you're like, oh well, I have to keep going. But hold up, we've done these before. Once you get to something you've seen before, but that's the problem. Is trying to remember. Like, oh yeah, that's right, I've seen this before. Okay, so case 4. And really, I'm just going to show you what to do. So that was the answer to that. I checked it. It's good. Actually, I didn't just now check. Just in case. So if somebody at home's like, that didn't work, this is what I got that Wolfram Alpha said was right. I think this is the same thing we just wrote down. This Wolfram Alpha says that's right.
Yeah, I think that was.
And that's what I just wrote.
Yeah.
Okay, so that's good. That's good. Now, case 4 was you had multiple irreducible quadratics. So what you do, and I'll just show you. So let's say this is your integrand here, x minus 1 squared, and you have something that's irreducible. X squared plus x plus 1 is irreducible. How do you know it's irreducible? You look at it and you go, can I factor that? And you say, well, hold up. Negative b plus minus the square root of b squared minus 4ac. So you go, okay, 1 squared is 1. Minus 4 times a is 1 times c is 1. That's negative 3. So you have this in there.
Yeah.
You ain't reducing that.
Yeah.
Not without getting complex numbers, and then, boy, yeah, good luck. So, same thing as before. I like to start with the linear ones. If there's any linear ones down here, no matter what order it's written in, I'm going to start with those. And I'm going to say, okay, multiple linear ones. So that means I need some constant over the thing to the first power, plus some constant over the thing to the next, over the thing to the next power. And I would keep going up if it were like to the 5th. Hopefully it's not, because your life's going to be really bad. But, okay, so I did that, we're good. Now this guy, same thing. It's the same thing. So here you have it to the first power, x squared plus x plus 1 to the first power, and we have 1 less, 1 degree less, so that would be a cx plus d.
Yeah.
Then we bring him up to the next power, and we say, okay, x squared plus x plus 1 squared, and now we need a new one. And so CD, how about E and F? EX plus F. The next one, we're going up to 3, so we need another. So it's kind of the same thing. It's just, when you have linear ones, they're just constants. And when they're irreducible quadratics, you use linear ones. So x squared plus x plus 1. The EF, how about G and H? and good luck. Good night. That's how many is that? That's 7, 8?
Yeah.
8 variables. You're gonna have an 8. You're either gonna be solving an 8 by 8,
That would take.
or yeah. I mean, it's gonna take forever. As you can see, this is why I'm not doing this one.
Yeah.
Okay,
Just
just
we have a lot like this. Or
no, you shouldn't.
Okay.
So okay, there's one more thing I want to talk about. Number 53, I think I assigned 50. No, I'm sorry, 51. Number 51, I assigned. And this is something I don't think we talked about this. Well, hold on. We'll do, let me. So one that's just like it is number 52, and it has the same prompt. It says use integration by parts to get an expression on which you can use partial fractions.
Okay.
So it gives you this: x arctan x dx. So it tells us use integration by parts. Okay, let's use integration by parts. I need a u and I need a dv. What do you want to let equal u from this guy?
Arc. No, the x. I mean, yeah.
You want to use the x?
Wait.
So then du is dx,
Oh, yeah.
and so then the dv is arctan. And what is the antiderivative of arctan? Oh, yikes. Okay, okay. So maybe, and this is part of it, right? 'Cause this is what we didn't talk about, and I will be even more explicit in a minute. But okay, so what do you want to let equal the u?
X, and then D. No,
Okay,
we just,
then dv. Yeah, that's what you just did.
yeah, arctan.
So okay, arctan. And what's the derivative of arctan?
1 over this. 1 plus x squared.
There you go. Dx. And so, okay, dv is then what? Everything that's left over.
Oh wait.
Right?
X, yeah.
Right, we got to choose, we're choosing u and dv, and we're undo. So we take the antiderivative of that, and it gives me 1/2 x squared. So this thing turns out to be uv minus the integral of v du. uv is 1/2 x squared, arctan, minus the integral of v du. V has a half and an unequal amount. X squared is in the numerator. He's in the denominator. And now we're in the realm of this stuff, partial fractions. That's what it wants you to do. Now yours is a little bit different, and you might look at it and go, wait a second. So I'm going to do something that's similar to what you're going to see in the book, okay? And this is what we didn't talk about, I don't think. Maybe we did, but maybe we didn't. What would you do with that? It's funny because that's what we were just about to do. We're like, we can't do that. How would you do that? Use substitution? That's not going to help you. Right? And the thing that you're not thinking about is like, because if you're thinking integration by parts, you go, well, there's no product there, right? Because in integration by parts, right, you need a u and a dv so that you can basically, you're looking for this thing to be like x sine x. If you saw that, you would say, integration by parts, because what's in there is a product. But that's not the only time you should think of integration by parts, because this itself is a product. And so you could say, okay, I need a u and I need a dv. And so, well, obviously, I'm not going to let the dx be d. Let's just, what would happen if I did that? Okay, dx is du. So then, I guess d squared x, or it would actually, I'm sorry, dx squared. We didn't talk about that notation, but it would be the second derivative. Okay, now arctan. Then, well, that's what I'm trying to figure out, right? So it doesn't help me at all. So what we're going to do is this. We're just going to hack. This is. I think of this as a hack. I'm going to say, okay, if dv is dx, and u is arctan,
No.
what happens?
Then it's 1 over.
Then
1
du
plus x
is 1 over that, and then v is what?
Just 1.
How about x?
Oh, yeah.
Yeah, careful with that. Careful. And check, is the derivative of x dx? There. Okay, so uv v du. So uv, I'm going to write it as x arctan minus the integral of v du, which is x1 plus x squared, which we just saw you could do a u substitution. I didn't put my dx's. You could do a u substitution with the bottom, 1 plus x squared, du is 2x. Remember, just because you have a hammer in your hand does not mean that you need to use it. You could try to partial fractions that guy. Why? You know. Du 2x, so you get x 10 x minus a half is going to come out.
Yeah.
X is going to cancel that x, and I get 1 over u du, which is x arc 10 minus 1/2 log u, but u is 1 plus x squared. And so there you go, we actually can do it. But we had to be tricky, right? You think there's no product in here. Yeah, there's a product right there. And that's how, I don't think we did it in class, but it would have been really good to figure out what the antiderivative of this guy is. It's the same thing. You say, well, that's not going to help it. You could take the derivative of this thing, and it turns into something that's actually manageable, right? And that's kind of the idea. Take the derivative of this thing, right, like log, and then if we let dv be the dx, log x, the derivative of it, works out to 1 over x. The antiderivative of this, now that's really easy because when you do your uv log v, blah, you get this minus the integral of v du. Oh, that's just a 1. And so it's just dx. So it's just x log x minus x as a constant. It's actually doable. Whereas trying it the other way is not going to help, right? So this is, I wanted to stress this when we talked about integration by parts, but I didn't, is that sometimes just a single function by itself, you can use integration by parts and get some fruit out of it. Okay, I think that's all I have to say. Any questions? All right, excellent. I will see you Tuesday. Or wait,
Thursday.
Thursday.